We know from experience that things don't just move on their own. Rather, things need to be constantly pushed or pulled to keep going. Right? 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 No. Actually, it's exactly the other way around. Some people are annoyed whenever I bring up ancient Greek philosophers, but I do it for a particular reason. Rather, two particular reasons. First, what they said is some sort of common sense idea of how the world works, and as such, most people today still intuitively believe those things. And two, it's always wrong, and it's always good to start from a misconception. Before the scientific revolution, the most popular explanation of the world was formulated by Aristotle. Concerning motion, he held that on the one hand you had the natural motion, which is what things do on their own, mostly being at rest. And on the other hand, there is violent motion, which needed a constant push or pull to keep going. Now this sounds plausible to us because it agrees with experience. As soon as you stop pushing something, it stops moving. However, there are things that don't stop moving as soon as you let them go, even over great distances like throwing an object or shooting an arrow. What about that? Galileo Galilei found a very interesting answer to this based on one of his experiments. He observed that if a ball rolls down a slope, it will roll back up the same slope again, almost to the same height. And the more you reduced friction, the more closely it would reach the initial height. Now, what would happen when you reduce the inclination angle of the uphill board? The ball would keep moving further and further so that it would still reach the same height. And if you keep making the angle smaller and smaller, the ball would go further and further, until it would go on indefinitely for a completely level board. Galilei called this idea inertia, and it turned our entire thinking of motion upside down, because things don't naturally stop, they naturally keep going. Aristotle was right about one thing. There is a natural state of motion, but it is that things remain in the state they're in. There is no natural resistance against motion per se, but against a change in motion. An object at rest will tend to stay at rest. An object in motion will tend to stay in motion. That's why what keeps things moving is the wrong question, because motion does not require an explanation, only change in motion does. Why does a pushed object stop moving as soon as we stop pushing? Well, mostly because of friction and gravity, so force is acting on it. Motion in the absence of force is not just possible, it is completely natural. We just don't see it so much because everything around us causes friction. If you go into space where there is only minimal friction and gravity, a thrown object will go on basically forever. That's how space probes like Voyager are still going after decades. They don't need thrusters to move, they just keep moving on their own. And this difference between Aristotle and Galileo isn't just semantics, it has different consequences which can be measured and observed. Okay, this is now the right time to return to a question from a previous video. A bowling ball accidentally falls out of the cargo bay of an airliner as it flies along a horizontal direction. As observed by a person standing on the ground and viewing the plane as in the figure at the right, which path would the bowling ball most closely follow after leaving the airplane? Inside the plane's cargo bay, the bowling ball is moving at the same speed as the plane. But what happens when it's dropped? Well, first it would of course drop to the ground because of gravity, and it would accelerate in doing so. But also, due to inertia, it would keep moving at the same speed it was moving before, at the speed of the plane. You can see that nicely when looking at photos of planes dropping objects. The bowling ball would experience air drag and so would slow down, but the principle still holds. It would keep moving forward in the direction the plane is going. So answers A and B are wrong. The correct answer is D, because of how this forward motion due to inertia interacts with the downward motion due to gravity. The forward motion always remains the same, while the motion downwards is being accelerated. When you combine these two facts, you get a parabola shape, so answer D. We can also watch this in a real-world example. The key concept is that all objects that are connected move at the same speed and continue doing so once they're disconnected. And that's why when you sit on an airplane or train and you drop something, it falls down to the floor and it doesn't just shoot back just because it leaves your hand. And that's also the reason why you can feel the rotation of the Earth, because not just the Earth is rotating, but everything on it too, including the atmosphere. The thing is, when you're going in a car or a train or a plane, you don't really feel the velocity. You only feel the changes in velocity, like the acceleration or a braking maneuver. You can also feel the effects of inertia when changing direction. So for example, a car driving into a curve. Your body attempts to keep going straight forward, but the car forces you into the curve. So you always feel like something is pushing you outwards. Galileo's law of inertia has later been adopted as Newton's first law of motion, and it goes like this. Every body perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. Note here that the distinction between being at rest and moving uniformly straight forward is not fundamental. Rather, you can treat being at rest as moving with velocity zero, so you don't need a special clause for that. Ultimately, it all depends on what frame of reference you're using anyway. So a moving plane to an observer on the ground is moving, but to an observer on the plane it is being stationary. Velocity is always relative, it's just a matter of perspective. To characterize this state of motion, we define a quantity called momentum by setting it equal to mass times velocity. Mass, or inertial mass to be precise, is the measure for inertia, so how much resistance there is to a change of motion. Inertia is the name for the concept. Inertial mass is the measurable quantity associated with it. And why is this useful? Because now we can state the law simply as momentum is constant and can only be changed by forces. Note that velocity has a direction, so it is a vector, and therefore momentum also is a vector pointing in the same direction. Any change to this vector requires a force, so both an acceleration or deceleration, but also a change in direction. Inertia will only cause moving in a straight line. Any other form of motion must be due to forces. Einstein's theory of general relativity has added an interesting facet to inertia. Its basic tenet is that things always move on a locally straight line. They just move in a space-time that can be curved, so their trajectories can also be curved as a consequence. So simple inertial motion is way more common than we thought. Remember though that inertia is not an explanation, it is a description. We observe that objects behave this way and we call it inertia. But that's just a word, it doesn't explain why things do that. Maybe we'll find it out in future, or maybe the universe just is that way and there is no deeper explanation for it. Either way, remember, things always want to keep moving. It's just that other things may prevent them from doing so.